So my pleasure to introduce our second speaker today, Léo Jimenez, who will be who's currently at University Claude Bernard in Lyon and is beginning a postdoc at the Fields Institute. His title is The Canonical Base Property in CM-Triviality.
Okay, well, thank you for the introduction, and thank you for having me as a postdoc and giving me the opportunity to talk. And yeah, so the title is indeed The Canonical Base Property and CM-Triviality. This is joint work with Thomas Blossier, and the Fields Institute here should go next to the University Claude Bernard Lyon. I just made a mistake, right? I'm not co-authoring this with the Fields Institute. Anyway, so let's get started. So first of all is the just setup that I will use here. So T will always just be a complete superstable theory of finite Lasker rank, eliminating imaginaries, and I'll always just fix a monster model where I'll just always work. So it's just like some quality of life setup, basically. Okay. So before I start on the CBP and CM-Triviality, I'll just remind everyone of one-basedness, which is actually a notion that's sort of very important in geometric stability. So a theory T is one-based if for any AB, the canonical base of the strong type of A over B is algebraic over A. Okay. So this has some very strong consequences on T. So basically T has to be like a pure set or have a definable infinite. That should be infinite here, of course, abelian group. But if you get out of the one-based universe of stable theory, there's no like structure theorem, right? For a while it was believed that any non-locally modular, non-one-based, strongly minimal set must interpret an algebraically closed field. But this was refuted by Rushovsky, right? Who constructed a non-one-based or non-locally modular strongly minimal set that does not even interpret a group. So it really just fails drastically, and since then, there was a lot of structure constructed that fails this. Okay, so what I want to do today is look at two generalizations of one-basedness, the canonical base property and CM-Triviality, and sort of see how they interact and what can be said about is there a structural result for this generalization for the canonical base property in particular. So that's the plan. So before I define the canonical base property, I must define internality for you. So we start with P, a family of types over small sets of parameters. I should have said that here. So we take a stationary type P over A, and we say that it's P internal, or almost P internal, if there are three things. So a set of parameters C containing A, a realization A of P independent from C over A, and a tuple of realizations of type in P which are based over C. And that means the type of EI over C is a type in the family P. And then we ask that A is in DCL of E and C, or in the case of almost internal, in ACL of E and C. Okay, so if this is the first time you're seeing this, it might be a bit like scary, but really it's not that complicated. So the standard example of this is two-sorted structure, one sort for the complex number, one sort for finite dimensional vector space over C. So in the language of, abelian group for C and vector space for V. Then any type in the sort V is C internal by just picking C to be a basis of V. Right, so that's really what this is trying to say, this definition. It's sort of like a vector space. It doesn't have to be, but the intuition is this. Okay. So now the canonical base property is the following definition. So if I pick any theory T, it has the canonical base property, CBP, for any tuple A and B, with B being the canonical base of A over B, the type of P over A, so I swapped the two, is almost P internal. And for P, we pick the family of non-one-based Morley rank 1 types. Okay. So just, I guess what I want you to notice mainly is that this is sort of a direct generalization of one-basedness. We just replaced algebraicity by almost P internal. So that's the sense in which it's a generalization of one-basedness. Okay, so I put it here, one-based implies CBP. And so the nice thing about this is often in algebraic examples, and like the two main examples here are CCM and DCF0, this family P is just an algebraically closed field up to non-orthogonality. And so, for example, for DCF0, this has like proving the CBP for DCF0 has really strong structural consequences. So it yields a very quick proof of, for example, like the dichotomy, Zilber's dichotomy for DCF0. This was by Pillay and Ziegler.
Leo? There's a question, Leo.
Yes, I can hear you. What's the question?
Hi, thank you. Can you remind us what is a one-base type? You find one-base here, right? What's the one-base type?
One-base type. Yeah, it's the same property except to replace, except you walk over the parameters that are needed to define the type, right? So you walk over A if the type is over A, and then you walk with realizations of the type instead of anything in the field. I think that's the proper generalization. And for strongly minimal type, it's just non-locally modular. It's the same thing. Was that the question?
Yes.
Okay. Good. Right. So, okay. So once we're there, we have this CBP property that's a generalization of one base. The question becomes, okay, you know, are there any theory that actually don't have it? And this was actually sort of, I guess, harder to answer than it should have. I don't know. It was not trivial to answer, I guess. So I'm going to present to you the first counterexample to this. So this is the Trushovsky, Palacin, and Pillay. So the structure is given by a sort for the field of complex numbers, and then a sort for C times C, with the projection only on the first coordinate, the action on C on the sort S, which is just defined by addition on the second coordinate, and then for every irreducible variety W of Kn that's defined over QAlg, we add a predicate for the tangent bundle of this variety, which is in the sort S, right, in the nth product of the sort S. Okay, so this does not have the CBP. So now this was actually the only counterexample that we had for close to 10 years, I think. And so this year, two new families of counterexample were constructed, and they're both very different from each other. So the first one was by Michael Losch. And so what he did is he still works over the complex numbers, and he basically explored the theory of this sort of covers of the complex numbers to develop new counterexamples. And his work is very nice. And then there's Blossier and I, Thomas Blossier and I, we did some work over another strongly minimal set. And we did something more like kind of brute force, just to have a counterexample. Very, very different work. Okay, so what I want to discuss before I talk about the work of Thomas and I is what makes this counterexample work. Like, what's the essential property of this that makes it work? Because it's going to be the same thing in our counterexample as well. So the essential property is that if I pick a derivation, any derivation delta of C, this map here, which sends AB to A and B plus delta of A, extends to an automorphism fixing the base or fixing the complex numbers. And basically what this allows us to do is to lift a configuration in the complex numbers that witness non-local modularity of the complex number to a configuration upstairs that witnesses non-CBP. That's sort of the idea of the proof. Okay, and more precisely, if you want to know exactly what happens here, what we lift, we just take a generic point of this variety here, x, y, z, w, which satisfy xz plus y, w equals 1, which is like the classic witness of non-local modularity for C. And then we take a generic point of the tangent bundle of this. This witnesses non-CBP in the theory. And we'll see that in our example with Thomas, we do the exact same thing, just over something else. It's really sort of funny. Okay, so that's it for the CBP and the counterexample. So now the idea is, how do we construct new counterexamples to this? Right. So, and the question that I really wanted to answer when I started this is, can we find a theory which doesn't have the CVP, that doesn't have an algebraically closed field? Or do we, for some reason, need a field? And because this is sort of a generalization of being not one-based, it's sort of a natural generalization of the trichotomy in a way. Okay, so how would we do that? I mean, the sort of naive idea is we start with non-one-based strongly minimal set. That does not interpret an algebraically closed field, of course. And then we just make a cover, just like Reshevsky, Palatin, and Pillay did, something that's still interpretable in the base set. And that's it, right? That's the plan. So how do we actually do that? And yeah, before I go on, just one remark. We would like this set to be actually a group. There's many reasons for this. The first one is that we want it to be Aleph1 categorical, and for that it needs to be a group. So this is a result of the Shazdakis, basically, plus some theory of binding groups. I don't want to get too much into this, just trust me on this. I'll ask questions at the end. Okay, so that's the idea. That's what we want to do. So here I put the definition of CM-trivial here just for completeness. I'm not actually going to use it, but I'm going to list what I want you to know about it. So there's this notion called CM-triviality for stable theories, and three things are true. One-based implies CM-trivial. A CM-trivial theory cannot interpret an infinite field, and a theory interpretable in a CM-trivial theory of finite rank, this is important, finite rank, also is CM-trivial. Okay. So this is another generalization of one-basedness. So now we are looking for a non-one-based CM-trivial strongly minimal group. Okay, so as far as I know, there's only one, but maybe there's others that I'm not aware of. But for me, that was only Bodish's group. Right, so now what I'm going to do is explain to you in, I think, 2 slides what this is. It's going to be a bit dense if you've never seen it. So bear with me. Okay, so we first fixed a finite field, k equals fq. And instead of actually working with Bodish group, I'm going to work with what I call Bodish Lie algebra, which is basically the more natural structure for me instead of the group. So, so first I define a 2 nilpotent graded Lie algebra. So this is a graded K vector space, V equals V1 plus V2 with a bilinear map. V, so then goes to V squared to V2. So the two second gradation parts, such that V1 wedge V1 equals V2 and V wedge V2 equals 0. So this is a Lie algebra. I'm just not using the Lie bracket notation. I got used to this wedge notation, but this is just the same thing. Okay, so there's a big wall of text here, but it's not actually saying much. So any 2 nilpotent graded Lie algebra basically can be viewed as a quotient of the free 2 nilpotent Lie algebra on the degree 1 part. So this just means we take a vector space V1, and then we construct the free 2 nilpotent Lie algebra, and then we quotient by the equations that we want. That's all this means. So I think, and these equations that we quotient by, we denote them by n of V, where V is our Lie algebra. So I think it's maybe more instructive to look at the example here. So just take any 4-dimensional K vector space A, generated as a vector space by A1, A2, A3, A4. So the free Lie algebra have 2 of these generated as a vector space by the AIs, and then the AI wedge AJ for I less than J. And that's it. No other relations. We just freely generate it, and because it's 2 nilpotent, that's all the wedge products that we have. Okay, and then we can form another Lie algebra by quotienting by this relation, A1 wedge A3 plus A2 wedge A4. And so the n of A here is exactly the vector space generated by this relation. So that's all there is here. It's a lot of text just to say we can quotient by equations. Okay. So the way the Bodish Lie algebra is constructed is by amalgamating finite dimensional two nilpotent Lie algebras. So let me quickly talk about amalgamation. So first, we need a prime-dimension function to amalgamate. So if I have a finite two-dimensional nilpotent Lie algebra, we define the pre-dimension of A and denoted delta of A by the linear dimension of A minus the linear dimension of n of A. So n of A were the equations that we were presenting by. Okay. So now that we have this, we have the classic definition of strongness for amalgamations. So we say that A is strong in B, and we write A less or equal B. If for any C between A and B finitely generated over A, we have that delta of A is less than delta of C. Basically, the delta, the prime dimension, doesn't drop when you go up. Okay. And now we define the class K. So the class K is made of all two nilpotent K Lie algebra A such that, moreover, for linearly independent A and B of degree 1, the wedge product is not 0, and delta of B is greater or equal to 1 for any non-zero finite dimensional subalgebra B of A. Okay, and we denote K fin the finite dimensional elements of K. Okay, so we're going to amalgamate all of these into a bigger Lie algebra. That's the plan. So, okay, so Bodish proves that K fin has the amalgamation property for strong extensions, and its amalgam is a two nilpotent FQ Lie algebra, so M1 plus M2 equals M, such that, okay, so these 2 points here just say that it is in the class K. And then it is also a rich structure, which means that if I take A and B in K, with B strong in K and B strong in A, then there is a stronger meaning of A in K. So this is just like a Frese limit. Okay, so this is omega stable of Morley rank omega times 2. Okay, so now Bodish collapses this into M mu, which is a Morley rank 2 structure. And I should add here that M mu 1, the degree 1 part is of Morley rank 1, and then M mu 2 is of Morley rank 2. Okay, so this is in K, but richness is not actually true. And so here I'm sort of sweeping under the rug some technicalities, but the intuition is richness is only true if the type of A over B is not realized too many times in B, and this is controlled by a function mu. And there's a lot of mu's possible, so a lot of different possible structures here. And this is actually a bit more complicated than this, but essentially that's what happens. Okay, so hopefully I've given you at least some idea of what is this Lie algebra. Okay. Now I'm just going to define the structure that we constructed, and it's going to look exactly the same as the structure of Polchowski-Palacin play. So we get a first sort, which is given by the collapsed Lie algebra, and then a sort S, which is V mu squared, and this is just the degree 1 part. I don't think I actually defined it anywhere. So this V mu is mu 1, the degree 1 part. Okay. So this is equipped with the projection, the group action of mu1 on the fibers. We also put the full group law on a squared. And then we add these tangent spaces for Lie algebras. Okay, so if we have a zero definable set in V mu 2n defined by these equations, then we add these equations here, which are basically exactly like the equations for tangent spaces in the case of fields. It's like a sort of transparent transcription of this. It's really the same thing. We just replace multiplication by the wedge. Okay, so the theorem here is this structure M is CM-trivial because it's interpretable in a finite rank CM-trivial structure, and it does not have the CBP. And so in particular, it does not interpret an infinite field. Okay, so this solves sort of both questions, right? First, we have something without the CBP that doesn't interpret an infinite field, and moreover, it's CM-trivial. So this is sort of the best thing we could hope for, actually, for not having the CBP. Okay, so in the time that I have left, I want to like sketch the proof of this, and then maybe end with some questions.
Sorry,
okay.
Question, Leo?
Yes. Right.
So base is just V mu is the base, not M. Is M mu play a role here or just V mu?
Yeah, so that's a good question. So so M mu is the base, yeah. But I think we could actually make it work with just V mu, and sort of instead of the wedge product, you'd have relation between elements of the degree 1 part, and I think it would work, but it's more convenient to work with M mu as the base. Yeah. So it's really, I think, more a matter of making the work easier to work with M mu instead of V mu as the base. I think it would work with V mu. Okay, so so the funny thing about this is once we have derivations, it's the same proof. Okay, so a Lie algebra derivation, that's just a linear map F such that f of A wedge B is A wedge f of B plus f of A wedge B. So just for fields, except of course the order here. I mean, this is not commutative, so you have to be a bit careful with the order. Okay, and so an observation that's like just a really easy computation is that if we have a derivation of M mu such that f of M mu1, so the degree 1 part, is still in the degree 1 part, then the map AU goes to A U plus f of A, extends to an automorphism of N, fixing M mu. And once we have that, if we construct enough derivation, we can prove that N does not have the CBP by considering basically the same configuration, right? So we have AU BV CR DS such that A wedge C plus B wedge D is 0, and then this is just the tangent, right? This is just the equation for the Lie algebra tangent bundle of this equation. This is the equation that I gave in the previous slide. So basically, the problem is reduced to how do we construct these derivations? Okay, so this is basically the hard part of all this. This is hard. Okay, so let me give you an example of why this is. So why is there something to do in constructing this derivation? So if we pick A, B, C, D in M1, this should be M mu here. The K here should be an M. So this is all notation that somehow stay here. And so we pick them such that A wedge C plus B wedge D equals 0. So that's the configuration that we want to use, right? Remember for the previous slide. And we want to be able to construct a derivation such that f of C equals f of B equals 0, and f of A is linearly independent of A, B, and C. And so if you work out the equation, this imposes f of A wedge C plus B wedge f of D is 0. Okay, so once f is defined on A, B, C, we have no choice for the value of f of t. Okay, and we have to handle basically every time this happens, right? And there can be many more complicated equations. Every time this sort of thing happens, we have to do something, right? We have to find the f of d that works. And so the idea is we sort of do a back and forth argument. So we start with a finite Lie algebra. We construct a slightly bigger finite Lie algebra with a solution, and then we amalgamate to construct the derivation. So to do that, we have to do quite a few things. So the first one is what I did here, right? So solve equations imposed by these plus the fact that we have a derivation, right? So find an f of d that works. That's the first step. Just find a Lie algebra that works. That's an easy step. The first hard step is to stay in the family K. So we need positive pre-dimension when we find a solution, and we also need that A wedge B is never 0 if A and B are linearly independent. So this is the first sort of hard part, because this can actually happen and you have to do some work to prove that you can sort of reduce to a smaller Lie algebra where this doesn't happen. And then finally, we have to make sure that we stay in K mu, so we have to control the number of realization of each type so that we stay in the collapsed Lie algebra. And this is also a bit difficult because it can happen that when you find a solution of your derivation, it adds an extra solution that you don't want to have in the collapse. And so you have to sort of do a quotient and show that you can sort of do it downstairs already. Okay, so that's the sketch of the proof and the sketch of how to construct these derivations. So now I just want to finish on 2 more questions on the CBP that I think.
There's a question in the chat. Do you need to check all possible codes for the collapse since your extension has a fixed size?
Sorry, can you repeat the question? I think I
You
didn't.
need to check all possible codes for the collapse since your extension has a fixed size. There are fewer codes which may be problematic.
Yeah, no, you need, so, right, so the way it works is, yeah, you need, so basically, if you have a code, right, for every code, you need to check that if you have like a B and then an A that realizes some code, you have to find a derivation that extends the derivation on B to a derivation on A, right? And this gives you another code, right, another extension. And so that's where the problem starts, right? That's where you could go out of KMU. I don't know if that answers the question or not. Does that?
Thanks.
Yeah, let's see, that's okay. So I see that does answer it. All right. Yeah. So two further questions before I stop. So the first one. So in their paper, Rushovsky, Palasin, and Pillay, so they conjecture or ask, I'm not exactly sure, that any structure interpretable in an algebraically closed field of positive characteristic has the CVP. So I would really like a positive answer to this. I think this would be really nice to see sort of a difference between positive characteristic and zero characteristic. It seems to have something to do with derivations. Of course, there's no derivation in a CFP, but that's sort of about it. That's sort of where the intuition stops for me. So I think that would be interesting. And the second question is, can we actually find something without the CVP that does not interpret a group? And again, I think it would be very interesting if you actually have to interpret a group to not have the CVP. I think that would really be interesting. And just something to note that I said again, something that doesn't have the CVP and that's not F1 categorical. Sorry, that doesn't have the CVP and that doesn't interpret a group cannot be F1 categorical, right? So it makes the math, like the model theory here, a bit more complicated. But a priori, it could exist. I'm not sure. Okay, so that's it for me. Thank you.
Thank you.